Thank you everyone for joining me today. Today I would like to talk about SolidWorks Sustainability, which is a life cycle assessment tool embedded in SolidWorks. Hello everybody, my name is Marlon Banta. I'm a director in the product definition team. I've been with the DS SolidWorks Corporation for over 20 years in the product definition team. I've worked on all kinds of products from simulation to rendering, core geometry assemblies, and of course, mesh functionality. But today I'd like to talk about SolidWorks Sustainability. So SolidWorks Sustainability is a lifecycle assessment product embedded in SolidWorks. We first implemented it in SolidWorks 2010. And around that time, I got my master's in environmental management and sustainability at the Harvard Extension School. And since then, I've become an adjunct lecturer at the Extension School. I teach 2 classes on greenhouse gas accounting. I've also done product definition consulting with the Climate Registry. And for me, my passion is sustainability. And so it's very good to work for a company like Dassault that is so heavily focused on sustainability and keeping a high ESG profile. So just to note, all of the presentation materials can be downloaded from this link. It'll include this presentation, the tutorial that we'll use, and also the required models. The agenda is we're going to review life cycle assessment, trying to understand what life cycle assessment means. In part 1, we'll do the initial assembly analysis. In part 2, we'll talk about analyzing parts. Part 3, we're going to review the environmental impact results, so understand what the calculations are in a life cycle assessment and SolidWorks sustainability. And then in part 4, we'll take our first attempt to reduce the environmental impact. We'll look at how SolidWorks sustainability is integrated with the assembly visualization tool. We'll talk about changing materials to reduce the environmental impact and also how we can change the part geometry to reduce the environmental impact. So first, let's talk about life cycle assessment. So what is life cycle assessment, or LCA? LCA is a technique to assess the environmental aspects and potential impacts associated with the product, process, or service by first developing an inventory of the inputs and releases to create this product, process, or service. All of the materials that go in, all of the materials that need to be disposed of, either generated during, say, manufacturing of a product or the end of life for that product. These inputs and releases can be energy inputs, and they can also be material inputs and releases. After developing this inventory of inputs and releases, also known as the life cycle inventory of the product, LCA then moves on to calculate the environmental impacts of each of these inputs and releases and aggregates those environmental impacts into an overall score for each of the environmental damage categories. And we'll talk more about what that means in a bit. The last step in a life cycle assessment is, of course, to interpret the results. To give an example of performing a life cycle assessment and developing a life cycle inventory, let's consider a simple example of a paper cup. So we have all of the inputs that went into creating the paper cup. We have the paper cup itself, and then all of the material and energy releases from that paper cup. And we'll consider a typical scenario of, let's say, a customer going to a coffee shop, purchasing a cup of coffee, and then disposing of the paper cup. We have inputs on one side and then releases on another. And so in this example, it's 5.7 grams of paper sent to a landfill, and that would be the release. And so what are the environmental impacts associated with that? In the United States, it is common for food containers to only go to landfill or incineration and not be considered for recycling. In some other areas, they are considered for recycling. On the other side, on the upstream side, we have the inputs that went into getting this paper cup to the customer at the coffee shop. Let's say the coffee shop kept the paper cup in a climate-controlled room for 12 weeks so it wouldn't get moldy or damaged by the elements. And that paper cup was driven 1,200 miles by truck along with millions of paper cups in that truck. And so for this one example, we would consider 1 paper cup's worth of storage for 12 weeks at the coffee shop and 1 paper cup's worth of transportation by truck in our life cycle inventory. We can go one level back and say, well, the paper cup needs to be manufactured. And so we would have 1 paper cup's worth of bleach used in the process to take paper pulp at a paper manufacturing facility and use that to create a paper cup. And of course, there are energy inputs, and we would also consider equipment depreciation in this. And so in each one of those, there'd be one paper cup's worth of each of these inputs. And of course, you can imagine going one level back beyond that to level 3 and then level 4. And what tends to happen when you're developing a life cycle inventory and running life cycle assessment is that if you go more than 6 levels back, each of the individual contributors, and I should say 6 levels back or 6 levels on the other side if there's a complicated end of life process for this product. But if you go more than 6 levels back, what tends to happen is that each of the individual contributors tend to be very minute in their contribution to the life cycle assessment. Each of them contribute just a small amount to the environmental impact of the overall product. And so generally, a rule of thumb in life cycle assessment is to consider, within the first 6 levels or less in order to develop the life cycle analysis. Continuing on this example of a paper cup, each of these inputs and releases, they have an environmental impact. A common use for life cycle assessment, one, is to determine, find hotspots. So you create your life cycle inventory, run your life cycle assessment, and see that, okay, in these particular inputs or releases, there is a strong environmental impact, and so that's finding hotspots. But another common use for life cycle assessment is to compare multiple products or different products or different processes even, and see which one has a lower environmental footprint. In order to do that, we need to talk about the concept of a functional unit. And so the functional unit is the thing that makes these seemingly different products similar. So in this example, we're considering a styrofoam cup, a paper cup, a ceramic mug, a plastic tumbler. All of these we're considering to be similar. And in order to truly make them similar, we would need to define the functional unit. In this example, the functional unit is the ability to carry 12 ounces of hot fluid for 3 hours, 300 times a year. So we're going to consider one person's use of these containers for 1 year. And so you can see right there that that functional unit makes them similar, but the inputs are very different. We would need 300 styrofoam cups or paper cups to match that functional unit. Whereas hopefully we'll only need one ceramic mug or one plastic tumbler. But in addition, we would need to wash the ceramic mug or plastic tumbler on a rather regular interval. And so in each scenario, we would develop a life cycle assessment and compare the environmental impact between the different products. Here is where SOLIDWORKS Sustainability comes in, because SOLIDWORKS Sustainability is a life cycle assessment tool. When we talk about life cycle assessment tools, software products, there's really 2 components. First is a large database of the environmental impacts of each input and release. And you almost want to consider these to be a PhD dissertation's amount of work to develop, to understand the environmental impact of, let's say, 1 kilogram of aluminum or 2 pounds of paper or a certain amount of cement used in a certain region. There's many variables that go in to understanding the environmental impact of a particular element that would go into a life cycle assessment. We call those elements human activities, and they can be things like material, or let's say transportation by truck, or electricity consumption, or all of the human activities that go into creating a product, process, or service. The other half of an LCA software product is the user interface that aggregates and analyzes the environmental impacts and helps you develop your life cycle inventory. SOLIDWORKS Sustainability is based on a database from a company called Sphera that is commonly used in the Gabby sustainability software product. Gabby has been a product for many years, and it's had many owners in the past. But Gabby is known in the industry as having a very comprehensive and well-trusted, accurate LCA database. So let's jump into SOLIDWORKS Sustainability, and we'll do part 1 of the hands-on presentation. And in this, we'll focus on assembly analysis in SOLIDWORKS Sustainability. So on the right side, we see the tutorial that we'll be following in SOLIDWORKS Sustainability, and I have um, SOLIDWORKS 2003 SB2 up and running on the left side. I've loaded this fire engine model, and I've also started SOLIDWORKS Sustainability. So you start SOLIDWORKS Sustainability by coming up here, Tools, and then Sustainability. I believe it's also available here in the Evaluate tab as well. Again, this model and this tutorial will be made available through the link that I've shared. So we've opened the fire engine launch SOLIDWORKS Sustainability. I always like to press in this push pin. And the first thing that we want to do is establish the assembly region. And so we're going to say that this thing is assembled in Asia, and it is built to last 5 years. And we're going to uncheck energy required for the assembly process. So, I'm sorry, I'm going to make sure it's unchecked. This allows you to define whether or not energy is used in the assembly process. And so we're going to assume that all of these plastic parts come together and they're assembled by hand in the assembly region. So we will uncheck this. But of course, you could define it's electricity or natural gas that's required and how much electricity or natural gas is required. And again, all of these are what we call human activities. So activities that go on, that are required to create this product. So for the use phase, we're going to say it's used in North America, and we're going to say that it requires 0.012 kilowatt hours of electricity per use. So this is a battery operated product, and that's the energy attributed to charging the batteries. So here we're saying it's 1 year of a toy's C-size battery must be charged 10 times. So continuing on, we're going to say that there are we'll remove the truck transportation and say that there is 12,392 kilometers of ship transportation that takes place. And for end of life, we'll say that only 7% of the materials, or 7% of the time that this product is disposed of, will it be recycled. We'll keep incineration at 13% and say that 80% will go to landfill. So those default values were based on EPA estimates, but we do know in the United States that we tend not to recycle plastics as often. And so the recycling rate for plastics is very low. And we'll say the duration of use is expected to be 1 year. So what we've done is we've defined human activities for the top level assembly. We've defined where it's manufactured, how long it's built to last, where the use region is, the energy used that is consumed during the use phase, any transportation, and its end of life treatment. In the tutorial that I provided, there are notes where you can read more about the particular, where you can read more about the human activities themselves that we've defined in part 1. So before we get to part 2, let's jump back to the slides. So one thing to note is you saw that I had built to last and duration of use defined as 2 different parameters. In this example here, we're looking at a car. And so you can imagine that the duration of use to be 10 years for this car. We will only need to consider the environmental impacts of 1 chassis, right? Because that is built to last longer than the duration of use. But we will need to multiply the environmental impacts of the tires by 2 because they're built to last 5 years And again, the duration of use of the car is 10 years. So you'll need to buy 2 sets of tires to match the duration of use for the car. And so that is the relationship between built to last and duration of use. Another thing to note is I wanted to show you how we calculated the energy use for the product. We went to Duracell's website and looked up the energy consumption required to charge a C-size battery. So, we have this voltage and this amperage, and came up with the value of 0.012 kilowatt hours per year as the energy required to charge that battery. Okay, so let's hop back into SOLIDWORKS Sustainability for part 2, and we'll look at the analysis that we would run for a part and show how we would establish the human activities for a part, and also show how the environmental impact is calculated for the part. So going back to SOLIDWORKS Sustainability, we're going to select, just to show you one way in which how SOLIDWORKS Sustainability behaves, is you can select subassemblies, either here in the feature manager tree, and you'll see the components from that subassembly. You can also select individual parts, and this is the analysis for that part. If you open the part in its own window and run SOLIDWORKS Sustainability, you will see the analysis for that part. So in this example, we're going to select rear axle assembly from the feature manager tree. And you can see all of these, all of the components that make up this rear axle assembly here. And you can see that we have the material name is set as, you can see asterisks there because we're using multiple materials. Most of the parts are made out of ABS, but for one of the parts, it's a low to medium density polyethylene. And so if we want to go back to analyzing the assembly, we can, of course, click back here in space. And now we're going back to analyzing and defining the human activities for the assembly. So the next thing that I want to do is I'm going to select the chassis. And here you can see that the material is currently set to ABS plastic, but we want to set the material class to be aluminum alloys. And we're going to pick a particular aluminum. And I'll show you exactly why we picked that aluminum in just a second. But we're going to pick that particular aluminum because some of the materials in SOLIDWORKS Sustainability have the ability for you to input the percentage of recycled content. And so that has the impact of reducing the environmental impact of using that material when you increase the percentage of recycled content, because you don't have to go and mine the materials and process the mined ores to to create that material. You can simply use post-consumer or post-industrial recycled content. And so in this situation, we'll say that it's 20%. Now, again, not all materials have this ability. So if I went here to that aluminum, it doesn't have the ability to enter your own recycled content, and it's assuming 0% recycled content. And anytime in SOLIDWORKS Sustainability you change from the default, we highlight the background of the input panel to be yellow. So we're going to set the manufacturing region for this part to be Asia. It's currently South America. And we're going to say that it is a die-casted part, and we'll leave the electricity at 1.85 kilowatt hours per kilogram, 0 BTUs of natural gas. We'll set the scrap rate to be 2%, and the scrap rate basically means that if we create 100 parts, 2 of them do not meet spec and need to be reprocessed or or the material recycled or disposed of in some way. We're going to set it to be no paint. And then we're going to select the use region to be Asia and set the truck transportation to 1,600 miles. And so this is a default. And we're going to change the recycling to 33%, 13% for incineration, and so 54% to landfill. And so there we've established the human activities for the chassis part. We can go back to the assembly, and we're going to select siren and mirror siren, so these two parts right here. And we're going to set the manufacturing region to be Europe. We can go back to this assembly, and next we want to select the speaker. So I could click here, but of course I could also use this filter to, find the speaker right there. And we're going to change the manufacturing region where this speaker, I'm sorry, I need to pick speaker, I'm sorry. We're going to select the manufacturing region to be Japan. Now I can pick Japan here. It's kind of, it does come up. It's a little bit hard to pick sometimes. And so I could also pick it here from this dropdown. And so we'll go back to looking at the assembly. So I'm going to click out of that. There we go. And disable that filter, basically. So one thing to note when we're running part analysis is that parts have both a manufacturing region and a use region. Assemblies have an assembly region and a use region. When you're considering a part, the use region for that part gets changed to be the assembly region when that part is used in an assembly. So if I were creating a stainless steel bolt, my company could sell that stainless steel bolt to end consumers. And so the manufacturing region would be wherever that bolt's consumed, and the use region would be wherever the hardware store is where consumers purchase that bolt. But that bolt could also be used in an assembly. And so let's say, for the bolt being sold to an end consumer, the manufacturing region is Asia and the use region is North America. If I were to use that bolt in a product that's also manufactured somewhere in Asia, then the manufacturing region would be Asia, the assembly region would be set to Asia, and then let's say the use region is North America. And so what would happen is the miles between where the bolt is manufactured and where it's included in the assembly would replace the miles of when that bolt was sold to an end consumer, manufactured in Asia and used in North America. And then the miles from the assembly region to the use region would be added. And those would be the distances considered when calculating the environmental impact associated with transportation. So one thing that we noticed when we were changing the human activities in SOLIDWORKS Sustainability is that we had these pie charts at the bottom that were updating with every change to a human activity. And these pie charts are showing us the environmental impacts associated with all of the human activities that we have defined. And so let's explore more these environmental impacts. So the first impact is carbon emissions or greenhouse gas emissions. And the units for greenhouse gas emissions are carbon dioxide equivalent. So we know that there are 7 greenhouse gases that are considered prominent contributors to climate change. And the things like methane, nitrous oxide, refrigerants, also sulfur hexafluoride and nitrogen trifluoride, and of course carbon dioxide. And so rather than reporting each of those gases individually, we have these things called global warming potentials so that you could convert essentially from, let's say, methane to carbon dioxide. And what the global warming potential tells you is the um, how strong that particular gas is at causing radiative forcing or trapping heat in the atmosphere. So methane is, I think, about 28 times more potent at trapping heat than carbon dioxide. So in order to convert methane to carbon dioxide equivalent, you'd basically multiply the amount of methane by 28, and that becomes the carbon dioxide equivalent. And so this notion of equivalency, we'll see that many other times when talking about life cycle assessment. So the next environmental damage category or environmental impact is consumption of non-renewable energy. And the units for that are megajoules. And so we understand that consuming non-renewable energy that has an environmental impact in and of itself, but also if we consume non-renewable energy for one product, then we diminish the pool of non-renewable energy available for any other product. It is believed that we have surpassed a notion called peak oil. That is essentially saying that when we pass peak oil, most of the easily accessible oil has been extracted. And after that point, the energy required or the effort required to extract more oil increases dramatically. And we can see that. We're burning tar sands in Canada. They're looking to explore for oil deeper and deeper into the ocean. And so, the easily accessible oil is becoming more and more scarce. Water eutrophication is the next environmental damage category that we consider. And water eutrophication is a process by which there is an overabundance of nutrients that leak into waterways, and that causes excessive biological production, mainly in the form of algae growing quite rapidly. And that causes an overconsumption of oxygen, which in turn tends to choke or reduce the amount of oxygen available to other life forms in the water body and can kill those other life forms. Here we see fish that have been killed because of oxygen depletion in this waterway. The units, depending on the standard that you're using, are either phosphate equivalent or nitrogen equivalent. And so again, here's this notion of equivalency that we saw with carbon dioxide and methane and greenhouse gases. Both phosphate and nitrogen contribute to water eutrophication, and in an effort to report a single value, we use this notion of equivalency. The last environmental impact category in SOLIDWORKS sustainability is air acidification. And so air acidification is a measure of the amount of pollutants released into the atmosphere that will cause acid rain. And the problem with acid rain is that the pollutants react with water, oxygen, and other chemicals to form sulfuric and nitric acid. And the problem that is caused by acid rain is that it releases suspended poisonous minerals from the soil, things like aluminum and mercury. It can cause over time damage to plant life, and it can also cause damage to man-made stone structures. And again, we see this notion of equivalency. So the units can either be sulfur equivalent or moles of the positive hydrogen ion equivalent in measuring air acidification. We do also consider material financial impact, and we have developed a database of rather coarse spot prices for materials, and that database is updated on a rather irregular basis. And so certainly you can see, let's say if you were creating your product out of gold or silver, those prices tend to fluctuate rather significantly over time. And you may see that our values are, perhaps in your version of SOLIDWORKS, are not up to date with what the current material spot price is. So let's go back into SOLIDWORKS sustainability and proceed on to part 4. So part 3 was to review the environmental impact results. If we're looking at one of these environmental impact categories, you can always click in there and see how it's broken down between material manufacturing, use phase, end of life, and transportation. You can always come back here to home. And we also show that in this pie chart. So right now we can see that a big driver of the carbon um, impact or the greenhouse gas emissions for this product are driven by our material choices. Next is manufacturing. For air acidification, we can see that manufacturing is dominant. And you can even see these individual pieces of the pie by hovering your mouse over these different color regions. And again, if you want to see in a bit more detail, you can view that here. And home brings you back. We talked about different methodologies for calculating environmental impact. There's two. CML is a European standard, and Tracy is a standard developed in cooperation with the United States Environmental Impact Authority, the EPA. And you can see, if we're considering air acidification, that here it's moles of the positive hydrogen ion when we're using the Tracy standard, in kilograms of sulfur dioxide equivalent when we're using the CML or the European standard. And we see that there. Okay, so in part 4, we're going to look at our first attempt to reduce environmental impact. So what we want to do is we're going to establish set a baseline or establish a baseline. And with this baseline set, we're going to see the effects relative to this baseline of changing these human activities and allow this, and we'll use this as a method to see which changes to human activities have the most impact. So one thing we may want to consider is we think that this toy will be used in North America. And so perhaps we should manufacture the toy in North America and save on some transportation costs. And so we're going to change the assembly process region to be North America. And we can see that by default the transportation changes to truck transportation, and we'll accept the default distance traveled. And we can see that had a slight an impact on or a slight change to the environmental impact in that it actually raised it slightly, so about 1%. We'll talk a little bit later of how such small changes are not shouldn't be considered meaningful. So we can see that was not really a very impactful change to be made. So we're going to go back to Asia and see that the ship transportation updated to 12,392 kilometers. You can see that we got back to our baseline. Another thing that we might consider is, let's say that these are, we're close to the December holidays, and these toys are in very, very high demand. And an organization may consider, if they didn't plan for demand properly, they may have to consider transporting these products by air. And so what would be the environmental impact of that decision? We're going to turn off the shipping transportation, and we'll go the same distance by air. And in this example, we can see that across all the environmental impact categories, we've substantially increased our environmental impact. And now transportation is dominant, where in other areas, especially in carbon, transportation didn't quite have the same footprint. So considering again the idea that, well, maybe we got the transportation wrong, let's switch the assembly region back to North America. And instead of transporting it by truck, let's consider transporting the product by train. A lot of products are shipped by train in the United States. And we can see that had a modest, everything else stayed relative to the baseline, but had a modest impact on one environmental impact category. So our first attempts at changing the manufacturing region and changing the mode of transportation proved not to be so impactful at reducing the environmental impact of our product. The next thing that we want to do is show how SOLIDWORKS Sustainability is integrated in with the assembly visualization tool and show how it can help us to identify the most impactful parts of our product, process, or service, and help us define, where should we be focusing. So to start assembly visualization, we come here to evaluate and sorry. All right. We're going to start that over again. So to start assembly visualization, we go to the evaluate tool and you can launch assembly visualization here. So here we see it defaulting to carbon because we're currently running sustainability. And what it's doing is we can also have it set to, we can add another column, and come in here and edit that to be showing, energy or energy usage or air acidification or water consumption as well. So we can customize it on the different environmental impact categories. We'll just go ahead and clean that up and delete that column. So here we can see, if we're considering greenhouse gas emissions, we can see that the chassis is the most impactful component in this assembly. So it would make sense then to have the most impact at reducing environmental impact of this product, that we would focus on the chassis first. So to do that, we're going to select the chassis, and now we can change the human activities for that chassis. And so you'll notice that in a previous step, we had changed it from plastic to aluminum. Let's go back and change that to ABS plastic. And we'll come in here and make sure that the manufacturing region is set to Asia and that we're using injection molding. We'll accept these defaults. And when we go back to the assembly, we see that the chassis is still the most impactful part of the assembly, but its impact has dropped down dramatically. It was 1.5 kilograms of CO2 equivalent, and now it's dropped down to 3.12. And let's just make sure again that we have the that is injection molding. We can see if we change it to extrusion that has a an even greater that would reduce its environmental impacts even more. But in this example, the chassis is clearly an injection molded product, so extrusion is not a viable manufacturing process. So let's go back and change that to injection molding, and we'll accept the defaults for electricity and energy. So here we can see that we have made a meaningful reduction in environmental impact by changing the material used to manufacture that product. One thing that we can do to select materials is we have a tool. Let's go back and select chassis. We have this find similar tool. And you can use the find similar tool to find materials that are similar to the one you have selected. And you can define similar in these different ways. One, we could say, select any material of any material class, and we want something with the same elastic modulus, or let's say that we want any material with an elastic modulus greater than, than this value. And we can say select similar, and we're presented with many choices for materials of any class that have a greater elastic modulus than that value that we selected. Come back in here and we can limit our field even more and say, well, we're really only interested in plastics for some reason, and you can see that we are presented with a smaller set of choices. And so this is a tool that you can use to understand, to find similar materials. And when you select on a material, let's say we'll choose nylon, then we can see what the environmental impact of that material is relative to the original material that we selected. Again, in this case, it was ABS. And you can see that there are some quite impactful plastic. But we'll go ahead and cancel and consider that our model will be made out of ABS plastic. One thing to note is that we have seen changes in the environmental impact across the four environmental damage categories. When the change is plus or minus 10%, you can consider that change to be directionally correct. So you're probably going in the right direction, but it does not necessarily guarantee that the change that you made results in a quote unquote greener product. It's just an indication that perhaps you're going in the right direction. And the reason for this is, in the study of life cycle assessment, there is a relatively large amount of uncertainty and a large tolerance or margin of error in life cycle assessment. And so changes of plus or minus 10% are directionally correct. Anything less than that is probably in the noise. Changes of plus or minus 30% for a simple product are considered to be meaningful. And what I mean by simple product are, single material parts. So if we're making butter knives, the whole thing's made out of stainless steel, or bolts or nails, single material products, then a change of plus or minus 30% is meaningful. You have to see changes of plus or minus 40 to 50% for more complex products. And so I would actually submit that it has to be greater than 50%. Let's say if your product is a car or a motorcycle or an airplane or something like that. So for more complex products, more complex assemblies with multiple materials and manufacturing processes and things like that, you could consider that one product, one alternative is greener than another when the changes are at least 40% and hopefully higher. So if we go back to SOLIDWORKS Sustainability, let's look at another change that we can make. So the chassis, we've reduced the environmental impact of the chassis. We can look at, let's say, the environmental impact of this part, top main shell. So we can see here that the material for the top main shell is ABS plastic. And we're going to use find similar to find another plastic, because we want to use the same manufacturing process, another plastic that is of similar strength characteristics. So we want the elastic modulus to be greater than 1 times 10 to the 9, and we want Poisson's ratio to be at least 0.39. So when it elongates, we want a very similar characteristic. We're going to go ahead and press Find Similar, and we're presented with a list of plastics that have those same properties. If we go to this plastic, I'm sure I even know how to pronounce that. PEEK, we can see that that's not really a good choice, because across all environmental damage categories, we can see that's significantly more impactful. So another alternative, let's say, is high density polyethylene. And here we can see that this is, in fact, considered to be a less impactful material than ABS. So we're going to go ahead and accept that. And now our material is high density polyethylene. We click there and we see that we're further reducing the environmental impact of our assembly. The last thing that we're going to do is see the impact of changes to the model in reducing or changing the environmental impact. The relationship between the SOLIDWORKS model and SOLIDWORKS sustainability is that the volume of the model and the surface area of the model are read into SOLIDWORKS sustainability. So for each of the part, we read in the volume and also the surface area. And those two values, if we go here to, we'll say the rear wheel, we'll go to the chassis instead of the single part. Those two values are read into SOLIDWORKS sustainability. So the density of the material is multiplied by the volume to come up with the weight of this particular part, and also the weight of the material used, so how much material is used. And then we also use a surface area to calculate environmental impacts associated with paint. And we really added paint as environmental impact to show that overall, for most products, paint represents a rather insignificant environmental impact. I know that we all hear the stories of large airplanes requiring a ton of paint to paint the airplane. But if you consider the environmental impact of that paint and the painting operation compared to the environmental impact of mining aluminum and machining aluminum into the parts needed to make an airplane, you'll see that the paint, even in that situation, is not as significant as other components for the airplane. So again, we're going to say no paint, back to the assembly. And in this example, what we want to do is we want to reduce, let's say, the thickness of the top main shell. And we're going to do that. Let's go back so we can see the model. We're going to do that by editing this shell feature. And so if I come here and I edit the shell feature, we can see that the shell thickness is 1 millimeter. And let's say that through simulation analysis or even costing analysis, other analyses, we understand that we can change that thickness to be 0.5 millimeter and still maintain the desired performance characteristics. And so going back to there, when we've modified the top main shell, sorry, let's rebuild. Go back to the top level assembly. We'll click to update. We can see that by reducing the amount of material used to create this top main shell, by reducing the wall thickness, that we have also reduced the environmental impacts attributed to that part and also the overall assembly. And again, there's a few more notes listed here in the tutorial. One last thing to note is that what we've shown so far is SOLIDWORKS sustainability analyzing parts that have already been created. One way to use SOLIDWORKS sustainability to inform your design decisions before completing your design or even starting your design is to create a dummy part or a dummy assembly. And let's imagine this to be an assembly of simple blocks, and each of these blocks represents the components that you intend to include in that assembly. You can size these blocks to be very similar, low fidelity blocks to be very similar to the size of the end product, and you can even assign mass properties to them. And then you can use the human activities in SOLIDWORKS Sustainability and change different settings to try and understand what would be the most sustainable way to produce this particular product. It is very challenging to create an injection molded part and then go back and recreate that same part as a sheet metal part. But if you do this analysis before determining whether or not it should be a sheet metal part or an injection molded part, then you're doing the analysis in a way that can help inform your design decision and can result in an entirely different and more sustainable design. So a few closing remarks. There is a certification exam, the CSWA exam for sustainability. The recommended training materials, there's this self-paced training material, which is the Sustainable Design Guide, available on solidworks.com. The exam is 60 minutes long, and you need a minimum grade of 80% to pass. Here are lists of some of the references that we used in this presentation and also in the tutorial. And again, to access the presentation materials, please use this link. It includes this presentation, a copy of the tutorial that I used, which also has all of those notes, and the models that I used in this presentation. Thank you very much for viewing my presentation on SOLIDWORKS Sustainability.